Today, we're talking about one of the most common naturally occurring contaminants of groundwater in the United States and indeed in the world, and that is arsenic. It's a pretty common contaminant out there. A lot of people don't realize that, but it really is, and it's naturally occurring for the most part. We do have some man-made arsenic contamination out there, but for the most part, most contamination, arsenic contamination of groundwater is naturally occurring. And so we're going to talk today about the geologic occurrence of arsenic in the subsurface, the geochemistry, and how we build wells to avoid arsenic, and then the treatment methods. And we're also going to talk a little bit about the regulatory requirements too, because those have changed over the years too. Hey everybody, I'm Tom Ballard, the groundwater guy. So let's dive in on naturally occurring arsenic in groundwater. All right, get my slides going here. So um, we're going to look at a comprehensive guide, and this is really designed for small water utilities. That's my niche in the business, and we work with a lot of small water utilities on a lot of different issues. And naturally occurring contaminants is one of those things. Arsenic is a big one, of course, and so we see throughout the world, even and in places like India, a lot of wells are impacted with arsenic. So, but here in the U.S., we have some specific areas in the country, and we'll look at those that that generally have a lot of arsenic. In California, for instance, it's one of the top two or three naturally occurring contaminants in groundwater wells, and throughout the country. So that's what we're looking at today. So let's dive in a little bit. We're starting with an executive summary, and this is going to be kind of a deep dive here. There's going to be a lot of technical details, and so we wanted to dive in because, like I say, this is really oriented towards small water utilities, and so we're diving into the technical details because it's stuff they need to know. If you're just a domestic well owner, you can hang on and listen to the presentation too, and probably pick something up as well. But just so you know, this is primarily designed for small water utilities, and that's why we're diving into such technical detail here. So, first off, health impacts. Arsenic is a toxic, carcinogenic trace element, and it's actually a metalloid or a semi-metal, and it can cause skin lesions, various types of cancers like lung, bladder, kidney, and cardiovascular disease. So, and it is toxic at some fairly low levels. The EPA maximum contaminant level is 10 parts per billion or micrograms per liter. The actual public health goal is zero, although that's not an enforceable limit. They lowered it from 50 to 10 in 2006, and that's where that compliance requirement comes from. National occurrence, 7% of wells and principal aquifers exceed the MCL, which is naturally occurring arsenic of 10 parts per billion. Detections greater than 1 part per billion in greater than 50% of the wells in the U.S. So higher risk in the western U.S. due to some conditions we'll look at here in just a minute. The risk drivers, uh, aquifer geology, redox conditions, that's reducing oxidizing conditions. pH controls a lot of these things all the time. If you've seen some of my other videos, you see where pH really affects the mobilization of some of these constituents. With arsenic, competing ions, and groundwater residence time. That's really we did a recent video on fluoride, and that's really a big factor there. But it also is the same for arsenic. So the longer water resides in the aquifer and the slower it moves through areas that are contaminated with arsenic, then the more likelihood you are to see higher concentrations of arsenic. So source management, well profiling, selective screening, sealing off high arsenic zones, and blending can also it will often reduce arsenic before full treatment is required. So a lot of times We're going to try these strategies to uh, do the vertical profiling in our wells and build a well accordingly so we can reduce the amount of arsenic coming in that we're actually going to need to treat. And sometimes we can actually avoid treatment altogether, but wherever you can do to manage the source to reduce the arsenic levels, that's going to save you a lot of capital expenditure costs on treatment. And so it's really important. And we recommend, and we're going to look at that a little bit more here, but we really recommend when you drill a new well or even when you have an existing well that you profile the arsenic vertically and try to deal with that and cut down on the amount of arsenic you're bringing in from the source. And there's ways of doing that and reduce the concentrations to the levels you can while balancing production at the same time. So that's kind of a mass balance calculation we do where we have known arsenic contamination and other types of contaminants and treatment considerations. Most systems require oxidation of arsenic 3 to arsenic 5 prior to removal, and that just makes it easier to remove and handle chemically. And residuals handling is pretty critical because you remove arsenic through a treatment system. Now you're going to have a high arsenic residual, and that's basically going to be a hazardous waste. So you're going to have to know how to deal with that. All right, that's the background. So, geology and geochemistry of arsenic. And we have a diagram here and we're going to see this in two consecutive slides. The upper right here really shows the surface oxidation and absorption qualities of arsenic. And then the lower left shows the solution oxidation and adsorption. So we're going to talk about those here. But first, we're going to talk about natural sources and occurrence. So arsenic is present in over 200 minerals. A lot of people don't understand that, primarily in sulfide ores, the most common one being arsenopyrite. And that's actually fairly common out there. And that's got iron, sulfide, and arsenic in it. It is present as a solid solution in iron oxides like pyrite and fine grained sediments. Some of these dark shales and clays can have high arsenic components too because of the reducing environment. So it's really common in volcanic or granitic rocks, and that's where the arsenopyrite comes in. Metasedimentary formations like those black shales and I was talking about, and slates, and then alluvial and lacustrine deposits. So kind of a wide range of geologic occurrence here. So, and that's why we see so much arsenic out there is pretty amazing. When you go to places like India, where they have a lot of fairly young volcanics and stuff, that's where we see arsenic associated with over there in the Deccan Traps area and stuff like areas like that. That's where the high arsenic comes from over there. Um, so arsenic's released through mineral weathering and water rock interaction, and the chemistry is going to play a big part in that. And believe it or not, the biology plays a part in that too. We'll talk about that a little bit more. And sorption to iron and manganese oxides is a key control on mobility. So high risk geologic environments in the southwest U.S. We have the basin fill aquifers, like you get down in the Central Valley and down the Mojave Desert. Some of these dry lake beds and stuff are generally going to have high arsenic. On the eastern side of the Sierra, for instance, in California, you get the Long Valley Caldera and some of those areas down there, and we see high arsenic associated with those. And glacial and fluvial deposits in the upper Midwest. So that's another big area. Crystalline bedrock aquifers in New England and in the Appalachians, and then deltaic and alluvial plains like the Mississippi Valley. So once again, we got a wide range of geologic environments that we see arsenic in. So it becomes really hard to predict sometimes, and a lot of times we just need to analyze for it and look at the data before we drill and understand where if there's arsenic there and where it occurs. We did some drilling out in California in alluvial valley up in the mountains, and one side of the valley had high arsenic. The other side of the valley did not. So most of the wells we were trying to put in were on the low arsenic side of the valley, but we couldn't avoid it. So, but they were able to handle with wells on the low arsenic side and wells on the higher arsenic side. They were able to handle things through blending to get their arsenic levels down. And so that's kind of fortuitous there, but it does require some planning and some balancing things out in order to do that. So the key concept is arsenic is often present but immobilized unless geochemical conditions change. Understanding these conditions is critical for predicting and managing arsenic in water supplies. So even things like overpumping can tend to mobilize arsenic too. So a lot of times it's going to be immobile, but sometimes there's just going to be a certain base level of arsenic that's dissolved in the water, especially high residence time water. That you're going to see arsenic there, and but it's also going to occur, especially when we get into alluvium and sedimentary rocks. It's going to be associated with specific geologic horizons, and this is sometimes where our vertical profiling of the wells and proper well construction can really help to minimize the amount of arsenic we end up with in our well, subject to balancing that out with production capability. If your high production zones are also high arsenic zones, then you're probably going to have to take the water and deal with it. But we can balance those things out usually. But doing enough vertical profiling so you understand the profile of the arsenic and where it's how it relates to the geology, and then specifically design the well to minimize and seal off those zones that have high arsenic can go a long way towards reducing the arsenic concentrations in your well. All right, so mobilization mechanisms. This is where we dive in a little deep here. So, and that's the lower left-hand side of this diagram here. So, reductive dissolution, and these are important because the different geologic environments are going to determine which of these applies and what's going to be the dominant mechanism that determines how arsenic mobilizes in your particular situation. So first, we start with reductive dissolution. So, under anoxic conditions, anoxic meaning low oxygen and reducing conditions, microbially mediated reduction of iron 3. So, this is where the bacteria comes into play because they're going, the bacteria out there, and these are usually going to be iron related bacteria, have a role to play in reduction of iron 3, and that's going to dissolve minerals, including any arsenic that might be in that pyrite, for instance, of those iron oxides. So the the bacteria then plays a role in that. So it does require organic carbon as an electron donor, and usually if you have bacteria present, you're going to have that organic carbon as well. So if you have iron-related bacteria and you're in a environment where arsenic is suspect, you may have the bacteria that's actually causing the release of that arsenic into groundwater. So you want to do what you can to control that bacteria. Obviously, iron-related bacteria comes back. You can get rid of it, but it comes back, and so you're going to have to watch that as well. But no, that is a mechanism that relates back to the bacteria and the microbes in the well. So sulfide oxidation, introduction of oxygen to arsenopyrite and other sulfide minerals causes oxidative weathering, and that releases arsenic, often generating acidic conditions because the sulfate is going to produce acid conditions in the well when combined with hydrogen in the water. So you're going to get acidic conditions. So this is where pH comes into play. And the next one is pH dependent desorption. Alkaline conditions where the pH is greater than 8 reduce sorption affinity of arsenic to mineral surfaces, increasing dissolved concentrations. So alkaline conditions, the higher pH is going to reduce the sorption and leave it in suspension or dissolved, and so higher pH is going to get that oxygen in the water. Competitive anions, phosphate, silica, and bicarbonate can displace arsenate, and arsenate is arsenic 5 from mineral surfaces through competitive adsorption. So it's going to the phosphate, the silicate, and the bicarbonate is going to preferentially adsorb to the surface and release the arsenate. So that's what happens when and so you can see a complex picture of the chemistry here, and understanding the chemistry is really important to determine how mobile arsenic is in your particular environment. Evapoconcentration, arid climates, and long groundwater residence times concentrate dissolved arsenic in solution. That's why we see some of these dry lake beds in the Southwest having high oxygen or having high arsenic concentrations because the arid conditions, and a lot of these are closed basins. The groundwater is nowhere to go, so you have high residence times, and that's going to increase your arsenic concentrations. And actually, in those dry lake beds, you get all kinds of things concentrating in there because they don't have any outlets, and so it just sits in there and creates this uh, darn near toxic stew down there. So not good water. And if you're bordering those areas, then you really got to look at that and see and not only arsenic, and we're talking about arsenic today, but what other metals you have down there too. Fluoride is another one. Hydraulic and operational changes, pumping patterns, artificial recharge, aquifer storage, and recovery can shift the redox boundaries, and that's reduction, oxidation boundaries, and pH, and that can trigger arsenic release as well. So these are a bunch of the different mobilization mechanisms you got to keep in mind. So it does get complex, I got to admit here. All right, arsenic species. We have basically, for our intents and purposes, we have two species of arsenic we got to worry about: arsenite and arsenate. Arsenite is arsenic 3, and that's dominant in anoxic conditions, which are going to be low oxygen and a reducing environment. Um, Arsenic 5, which is arsenate, tends to dominate in oxic conditions, which are going to be oxygen rich, oxidizing environments. And so that they can flip back and forth a little bit depending on the pH and the redox boundary. So the comparison of the properties, mobility, arsenic 3 tends to be more mobile, arsenic 5 less mobile. Toxicity, arsenic 3 is a lot more toxic, arsenic 5 less toxic, although it's still toxic. The EPA's MCL does not differentiate between arsenic 3 and 5, by the way, so it treats them both the same. Sorption, arsenic 3 is weakly sorbed, which means it's going to be more mobile, and then arsenic 5 strongly sorbed to iron oxide. So it'll tend to, unless for some reason there's some geochemical situations there, it will tend to stay sorbed and probably not as mobile. And that's kind of what we're looking at up there. And arsenic 3 is going to be harder to remove. You're generally going to have to do some extra stuff in your treatment. Arsenic 5, much easier to remove. So, treatment implications, most treatment processes are more effective for arsenic 5 or the arsenate than arsenite. Pre-oxidation is often required to convert arsenic 3 to arsenic 5 before treatment so you can more easily get rid of that. So, and we can see some of the different compounds we have and the pH controls on those in this arsenic speciation graph here. But what I want to point you to is below here speciation or the pre-oxidation method. So this is converting in a treatment process arsenic 3 to arsenic 5 for easier removal. Generally, we're going to do some pre-oxidation to change the state of that arsenic to from arsenic 3 to arsenic 5. The most common one at a treatment plant is going to be free chlorine. Obviously, Most water systems are going to have plenty of chlorine on hand because they're chlorinating. So they can put that into the process and makes it a little bit easier. But other tools, potassium permanganate, for instance, ozone, and manganese dioxide as a catalytic media also work as well. So, um, all right. So EPA regulatory requirements. There's the timeline here on the right hand side. Just note that in 2006, the rules were finalized that moved it from the 50 to the 10 billion parts per billion, and that's where it is today. And I believe there's some states out there that do have lower MCLs at a state level, but I'm not sure on that. So, but the national level, the US EPA MCL is 10, and as I mentioned earlier, the public health goal is 0. So, but that's not enforceable. But that's the goal. So. Compliance monitoring is required at entry points to the distribution system, so quarterly or annual sampling based on the previous results. Obviously, if you've had previous arsenic results that are close to the MCL, they're going to require the more frequent monitoring. And you have to use the EPA approved analytical methods and a certified lab for those results. Reporting consumer confidence reports that all water systems have to produce for their customers must include arsenic information. Public notification is required for violations, like most things in the consumer confidence report. Flexibilities, variances, and exemptions are possible for small systems facing technical or economic challenges, but it does need to include a compliance timeline. And my understanding is those variances and exemptions are pretty hard to get. You have to really show a hardship and a specific plan to get back in compliance in a certain period of time. So, planning considerations, treatment technology selection, affordability, life cycle costs, operator training, and residuals management. And we'll talk a little bit more about the residuals management. I already mentioned that when you're removing arsenic from your groundwater source, that is then going to create a potentially toxic or hazardous waste that you're going to have to deal with accordingly. All right, national distribution and risk areas. You can see our map here of the United States, and you can see arsenic is fairly widely distributed. So, as we mentioned, our detection rate, 50, greater than 50% of the wells with detections greater than 1 part per billion across the U.S. Generally, 2.1 million people are affected by arsenic. In the western U.S., 16% of the wells exceed the MCL of 10 parts per billion, especially in the southwest basin filled aquifers. And the national average is 7% of wells in principal aquifers exceed the MCL of 10 parts per billion. So you can see it's a significant problem and it's pretty widespread. So it occurs in a variety of geologic environments, as we saw previously, and you can just see that from the map here. All right. Vertical profiling is one way to, and we always want to consider some way to avoid treatment if we can, because it's going to be lower cost. One way to do this is vertical profiling of wells, preferably as you're drilling them. If you do the vertical profiling and you look at both flow under dynamic conditions, which is pumping conditions, and under ambient conditions, which is non-pumping conditions, you determine the contribution of these different zones, and then you run a mass balance to determine which of these, the higher arsenic zones, can you screen off or seal off and still get a productive well that's going to reduce your arsenic inflow into the system. And that's really what the vertical profiling comes down to is we're going to sample our intervals and at a minimum 50 feet. If you're in a known arsenic area, I tend to like to go more than that. We got some tools out there now that allow us the old school zone testing. Really, I don't recommend that anymore. We have some tooling out there where we can really do some higher definition profiling and really nail things down. If you got a good geologic log, then you can tie that back to the geology and really come up with a good solid well design that's going to minimize the amount of arsenic coming in. You may not totally get rid of it, but you can minimize it using these methods. Um, so that's really what we want to do is we want to do the vertical profiling. We want to do a mass balance and calculation, and then design our well accordingly. So a lot of different ways to do that. We can do the flow measurements with a spinner flow meter, heat pulse flow meter, dye tracers. Um, there's a number of different methods for doing that. Um, Water sampling, you can do packers, hydraulic isolation tools, low flow pumps, a lot of different ways to do that too. But we want to do discrete intervals and build that profile of arsenic, tie that back to the geology, and design our well accordingly. This, if you can minimize your arsenic coming into the system by the way you build your well, it's not going to cost you that much more, and it's going to save a lot of capital costs down the road. So this is really the way to go if you're in an area where you have known arsenic concentrations. All right. Well designed strategies to avoid arsenic. Grab a drink here. Site selection. Know your geology ahead of time. I mean, you can go out and generally you're going to know if you're in a high arsenic area or there's some other arsenic detections. So you're going to want to do your homework. Whatever consultant you have working for you should be able to do that for you. Um, Avoid known high arsenic formations when feasible. Utilize existing regional groundwater quality data. Consider vertical stratification of the arsenic in the aquifer so we know what zones the arsenic is occurring in, and we can really look for those and log those when we're actually drilling the well. Um, Screen strategy, shorten the screened intervals, place screens only in low arsenic zones identified by vertical profiling. Consider multiple discrete screens with isolation packers or sealing off those zones. And this is going to be your vertical profile is going to guide you on this. The casing and seal design and install deeper casing and competent annular seals to isolate shallow reducing zones or problem strata and use proper grouting materials and techniques. You don't want any communication between the aquifer that has arsenic contamination and relatively clean zones. I've seen a lot of mistakes in this regard where people will they'll case off these areas, but then they have a gravel pack that extends all the way up to the surface, so you're getting flow through the gravel pack outside the well itself, and you're really not doing you may reduce it a little bit, but you're still getting communication between high arsenic and low arsenic zones. So you really want to be smart about how you design the well. Um, Gravel pack selection, pump placement. The pump placement can make a difference where you're drawing from and doing your testing, your some pump testing on the well before you finalize construction is going to be important for that and determining where you're placing your pump. And then pre-construction testing. You drill test wells, and you conduct a pilot profiling to inform your final design. I'm a big proponent of drilling pilot wells, not just all one go, especially if you're in areas where you have things like known contaminants like arsenic. You're going to want to drill a test well, do that profiling, and before you build the well and bring in all this expensive stainless steel screen and all that, you really want to have an understanding of building the best well possible. All right, modifying existing wells. This is really and we can go in and do this. It's a little more expensive, a little more complex than designing a well right in the first place. But sometimes due to varying conditions or changing aquifer conditions or pumping rates in an aquifer or a basin can bring arsenic levels up over time, and so you may be getting arsenic where you haven't before. So what we can do is we can look at our well and we can go in and we can do that same vertical profiling thing through our screen sections and determine which sections we might want to seal off. And there's ways of doing that. We can go in and we can do packers in the upper and lower, and then we can go in and squeeze concrete into the screen and seal those zones off. And you're going to want to get it above and below, ground that probably into a clay layer in between the aquifer, the high arsenic aquifer zone, and then you can effectively seal that off. Once again, you're probably going to want to do some flow testing and isolate the individual zones. And so you understand where your flow is coming from. So you basically don't seal off your most productive zone. And then you end up with low arsenic water, but at a minimal production capacity. So that doesn't do you any good. So the mass balance approach applies here as well. Um, but we've seen this work really well, especially for arsenic, because arsenic tends to occur in specific geologic zones that you can isolate. Now we've seen it where it occurs throughout, and that can be a little tougher. But where you have nice distinct zones that are showing high arsenic, then that just really lends itself to sealing that off, and really then to the point where minimal treatment or no treatment at all may be possible. All right, blending strategies. This is another one where you're not actually doing actual treatment, but you're actually taking high arsenic sources, blending it with low arsenic sources, and coming up with a flow that meets the MCL requirements. So that's you want to get under 10. You want to get significantly under 10 with your final blended water. Is basically what it comes down to. This can be a little tricky if you have well fields and you got varying levels of arsenic in there. So you're going to have to kind of do some calculation to determine how much contribution you want from each well at any point in time, and when you're running them. And sometimes we schedule wells, and so it can take a little bit of calculation to figure out how to do that. But then once you have it done and you've done the math, then you should be able to run it the same way all the time and balance that arsenic out so that you're coming in under the MCL and you don't need to do treatment. So um, it's lower cost and complexity than treatments, quick to implement, reduced chemical handling, minimal waste generation, and but it is vulnerable to source variability and outages. So you've done your careful calculations, and now your arsenic input changes for whatever reason. So you're going to need to monitor that. And usually the regulatory community is going to make sure you're doing, if you're doing blending as an option, then they're going to make you do sampling a lot more frequently. So that's something you're going to need, and you may need treatment as a backup anyway. And it can impact other treatment process because you're varying your chemistry a little bit too. So treat blending is a secondary to source control. You want to, if you can get your well designed properly. If not, or you can't strike that balance, then blending is a way to go. And then the last option then is to go to full treatment. So and you're going to want to validate that with pilot studies, seasonal profiles, because things can change seasonally too, and robust monitoring. That it's probably going to be required by the regulatory agency anyway. And here we got an example. Uh, we have source A well over the MCL at 20 parts per billion with a flow of 500 gallons per minute. You're blending it with water that is at 8 at 1,000 gallons per minute. And so you can actually get that down. And I don't, oh, I see. I'm sorry. I got this wrong here. So you got source B 2 micrograms per liter parts per billion with a 500 gallons per minute flow. Now our blended water is coming in at 8, still uncomfortably close to the MCL, but you're now at 1,000 gallons per minute under the MCL, so that should work. So I'm sorry for not having that right there. But that is correct. You got source A, source B, and then your blended water is here in the middle. So you come in, and that's just an example calculation, easy one. Sometimes you're doing 4 or 5 wells at the same time, it becomes a little trickier. So, all right, treatment technologies. Let's look at the different treatment technologies and some of the caveats there. Um, First one, and once again, these get kind of complex, so bear with me here. Coagulation and filtration for arsenic. Um, this is a treatment mechanism. Pre-oxidation converts arsenic 3 to arsenic 5 for effective removal. So you're doing that pre-oxidation generally with chlorine, and that's going to convert the arsenic 3 to arsenic 5, and it's going to make it easier to remove. You're going to use iron salts to form a hydroxide flock. The arsenate, which is the arsenic 5, is going to co-precipitate with or absorb to the iron hydroxide particles. And then you're going to get solid liquid separation via filtration, and that's going to remove your arsenic laden particles. So it's basically a coagulation and then filtration. So the optimal pH range here 6.5 to 7.5 for maximum arsenate removal. Your iron arsenic mass ratio is typically going to be 20 to 40 to 1, and you can do jar testing to optimize that. Um, Adequate mixing energy and fluctuation time is needed. You don't want to push this through too quick because you're going to have time for, you need to have time for the arsenate to adsorb onto the iron hydroxide particles. So, advantages and challenges, co-removal of other contaminants. So you're going to pick up some iron and manganese in this process as well. So, and that's often good because a lot of times these go together. If you got arsenic problems, a lot of times you'll have iron and manganese problems as well. So you can deal with them at the same time. It's going to be robust for variable water quality conditions, and it's an established technology. There are challenges with chemical handling, backwash management, and sludge disposal. So, and as we point out here in the box over here, residuals management, arsenic sludge from backwash requires proper handling and disposal. So you're going to want to conduct TCLP testing, and that's a toxic characteristic leach process. It's a special kind of testing that determines if it has hazardous waste criteria. And then if you have hazardous waste criteria, then it's going to have to be disposed of as a hazardous waste. And you're going to have to jump through more hoops with paperwork. And there's only certain places it can go, and it's going to be more expensive to dispose of. So that is the problem with removing arsenic, because now you're dealing with, the toxicity and you're concentrating it. Absorptive media treatment, the media types here are granular ferric oxide or hydroxide. That's going to be an iron-based media with high affinity for arsenate. That's the iron 5 again. And it provides 20,000 to 40,000 bed volumes before exhaustion. So that's going to be the number of cycles you can go through before it's exhausted, and then you're going to need to replace the granular ferric oxide or hydroxide. Hybrid iron media, that's going to be iron impregnated resins, combining benefits of ion exchange and absorption. And then activated alumina. This is actually an effective treatment for a number of contaminants. We recently looked at fluoride, and that works there too. The effective pH there is 5.5 to 6, so a little on the acidic side, and it has lower capacity than iron-based media. So probably you're better off going with the iron-based media, because arsenic has a natural affinity for the iron, as we've discussed, and so that's going to be a better option for you. So process requirements: arsenic must be in the arsenic 5 form. So if you have arsenic 3, you're going to need pre-oxidation like we did before. pH typically 6.5 to 8, so kind of around a neutral pH. Uh, Empty bed contact time 3 to 6 minutes plus for effective removal. So you got to make sure there's some residence time there. And lead lag vessel configuration provides breakthrough protection. So if you're getting breakthrough, you don't want to breakthrough. You want to have some backup. So basically, you're going to have a lead, you're going to have a lag, and any breakthrough that's going to occur is going to be in the middle, so you can monitor that before you get breakthrough on the end, and so you're protecting yourself there. So operation and maintenance, regular monitoring of breakthrough. Effluent arsenic typically increases gradually, so you're going to want to watch that and track that. Media replacement when exhausted. Some media can be regenerated with sodium hydroxide, uh, and then spent media testing, TCLP for non-hazardous disposal classification. The TCLP is going to tell you if it's hazardous or not and how you got to dispose of it. So performance considerations, as we mentioned earlier, phosphate, silicate, and sulfate compete for adsorption sites, and it reduces arsenic capacity by 30 to 50%. Pretreatment may be needed for waters with higher competing anions. So you're going to need to know your chemistry going into this and understand that if you have phosphate, silicate, and sulfate, you may need to pre-treat for those too. So you can start to see this can become a little bit complicated sometimes. So the benefits and the challenges of this are simple operation, modular design. It's effective to small to medium systems. So pretty much ideal for a small water system. The cons are the media cost and disposal, sensitivity to competing ions. So you need to manage those, and the pH dependency. All right, ion exchange and membrane technologies. These are going to be tools that are probably work for almost any contaminant. Ion exchange is usually going to be a resin that's going to exchange chloride ions for arsenate. That once again is your arsenic 5. If you have arsenic 3, you're going to have to um, treat that to convert it. So and do some pre-oxidation there. Um, the performance is going to be limited again by competing ions, sulfate, nitrate, total organic carbon is going to be in there as well. So you're going to have to once again monitor your water chemistry. So all these treatment techniques are going to require some. You're going to have a decent level of operator certification. And your operator needs to understand the sampling, what kind of balance you have to have, the chemistry. And so an entry level operator probably is not going to be able to do this for you. You're going to have somebody with experience with these systems. So that's important to understand. If you have arsenic, you're going to have a certain grade of operator to run one of these systems. RO, nanofiltration, high removal efficiency for both arsenic 5 and arsenic 3 with pre-oxidation, of course. And the typical recovery rate 70 to 85% of influent water. Uh, there's pre-treatment requirements for scaling control, particulate removal, because this is microfiltration and nanofiltration. You really need to make sure you're not clogging your screens is what it comes down to. And concentrate disposal strategy critical for sustainability. So ion exchange is favored for low sulfate silica waters, lower total dissolved solids. It's a lower capital cost. RO and NF favored for multiple contaminants, high TDS, consistent quality needs. And RO is probably going to be your most expensive as well. So once again, you're going to be dealing with brines in either case, and that's going to be concentrated arsenic and other contaminants in there that you're going to need to analyze and dispose of properly. All right, point of use, point of entry systems. There's a little caveat here, and I these can be useful, but a lot of times really small water systems sometimes will buy these for their customers and they take on maintaining them. That can be a potential legal liability. You gotta think about this, because if you get breakthrough and people are getting exposed to arsenic because you haven't maintained the system when you've agreed to, then you got some potential legal exposure there. So the best thing to do is to somehow make the point of use place, the point of entry, make them responsible for maintaining and testing and that type of thing. You may pay for it, but they're responsible for doing it. So there's some kind of release of liability. So that is my caution on point of use and point of entry types of systems. So these are going to be, small systems. Are usually going to be under the sink RO or some type of ion exchange. Um, Sometimes there's absorptive media cartridges, iron based or activated aluminum. Uh, that you can use, but a lot of time it's going to be RO, and so there are certain requirements. You're going to have professional installation to make sure it's done right. And if the water system is taking on responsibility for these things, you need to consider your legal exposure. So the compliance water, the access and the consent, the equity and the customer support. So you're going to need to everybody's going to need to understand those. So it's rife with some challenges. It can be a cheaper solution, actually, but because of the potential legal problems, I'm not a big fan of this, but it has worked for different people, I will say. So if you're a really small system, this could potentially be an option to look at too. So we got the program flow there. You need to look at the initial assessment and the individual situation and some baseline testing, educate the customers, and have an agreement with them so they understand who's responsible for what. The routine maintenance, the monitoring needs to be set up, and compliance reporting and documentation. You're going to have to document, and keep those documents. And that's how you protect yourself under this. So, um, EPA guidance permits point of use and point of entry systems for small systems when centralized treatment is not economically feasible. So it's important to show that because you're going to have to document that. Otherwise, you may get stuck with the capital costs of putting in a full blown treatment system. All right, residuals management. This is the tricky thing. Residual types, iron arsenic sludges, spent absorptive media, the ion exchange brines, the RONF concentrate, backwash from various processes. This is all these treatment processes are going to produce some waste that is going to have uh, concentrated arsenic in it. So you need to going to characterize that by the toxic characteristic leaching procedure, TCLP, um, and determine how to dispose of that. If it's hazardous waste, you're going to have to dispose of it under manifest and only at certain locations that can accept that. Sometimes people will evaporate these things out, so it's not a sludge, it's a dry waste, but it's still going to be concentrated arsenic, and you're going to need to dispose of it accordingly. So, um, handling methods, we just talked about that. So, I like the drying thing if you got room to do that because it produces a smaller volume and it's easier to get rid of in dry waste than liquid waste. So, um, cost factors. Um, you just got to look at transport distances, and this is stuff you're going to have to factor in when you're looking at a treatment plant for arsenic. Is how do you deal with the waste and the costs associated with that? So you're going to have to set aside operating expense. There's not only the capital expenditure of the putting in the treatment plant, but the operating costs that are going to have to go into your asset management plan and capital improvement plan. And you're going to have to look at that and a lot of these other factors, how you get rid of the residuals, is going to be an important part of ongoing operating expenses and is going to come into your life cycle costs for this. So, design considerations, we want to look at that. And you're going to have to anticipate seasonal variations in volumes and seasonal variations potentially in arsenic concentrations, even. So, sometimes fluctuating water table levels can concentrate or dilute the arsenic concentrations as well. So, safety and training, when you're dealing with hazardous materials, obviously the operator training is going to have, you're going to have to up that a notch, and they're going to have hazardous materials training and understand how to deal with this stuff. So, um, the management flow here, the residual generation, the characterization, the dewatering and volume reduction. That's going to be important because that's going to save you a lot of costs. Storage and handling, because potentially hazardous waste, you're going to have to store it and handle it a certain way, and then disposal and discharge. Um, so if they fail the TCLP and require handling as hazardous waste, then you're going to be limited in where you can take it to, and it's going to cost you more money to do that. All right, implementation roadmap and summary. Um, First off, you're going to do a baseline assessment. You're going to gather your historical data, conduct new sampling, including speciation. You're going to want to know whether you have arsenic 3 or 5, arsenate or arsenite, and you're going to screen for interferences. So you're going to have to understand the chemistry of the water, not just the arsenic, the iron, the manganese, but all these other things that can affect the absorption. Um, in your wells, you're going to want to do the vertical profiling, as we discussed earlier. Um, Preferential, if you can do source management, that's going to be preferential to treatment. So you're going to want to really look at that. And when you drill new wells, make sure you understand the geology and place them accordingly, so that you can minimize the amount of arsenic coming into your treatment plant. Pilot testing. If you're going to do a treatment plant, you're going to have to do some initial pilot testing. Make sure you get it right before you invest the big bucks in the capital costs. Um, Funding and design, you're going to need to understand what it's going to cost you, secure the loans and grants, calculate your life cycle cost. That's going to, be a big determinant. I'm not really big on looking at the initial capital cost. I like to look at the total cost over its life cycle. That's really the proper way to look at any capital investment. So, construction and operation, implement construction, conduct startup training. Training is going to be a key component. Develop your SOPs. Any data driven organization is going to have SOPs, going to have established processes, because you're not going to want to screw this up, because arsenic is toxic, and you don't want any legal questions if you're getting breakthrough and high arsenic levels exceeding the MCL in your drinking water source. You got potential legal issues there. So you want to make sure you have it right and you're checking and rechecking. So our key takeaway: start with the aquifer. That's going to be the profiling, the source management, and then choose simple, maintainable solutions appropriate to your system's technical capacity. Now, a lot of these treatment systems are going to require more than a simple operator's license, so you're going to have to look at that. And then monitor your KPIs. Those are key performance indicators. Those are the numbers that are going to tell us how we're doing. So, and it's, a single data point is a snapshot. We want to look at the trends. So we want to measure our KPIs and constantly looking at our trends. I take those, I put them in a spreadsheet dashboard where it charts me, and then you can look at the chart and know where you're at all times. So so some KPIs are the entry point arsenic. You want it under the MCL, the media run length, the chemical use, residuals volume. You want to track those trends over time. So, and over here on the right, we have our 6 steps here to operation, from baseline assessment through construction and operation. And that is the presentation. Let me go back here to my closing. All right, so that's what you need to know about naturally occurring arsenic in groundwater, and hopefully you don't have to deal with this. But if you do, we've laid out pretty much what your options are and logical sources. If you have any questions on this video or about arsenic and groundwater in general, my email is there. I appreciate any likes and comments on the video, and post those. That really helps with the YouTube algorithm. But if you have any specific questions you want answered, feel free to reach out via email. I answer all my emails, and I answer comments on the videos too on a regular basis. So feel free to do that. And until the next video, thank you very much for listening, and good luck.